Good morning to everyone, and that was John Denver leaving on a jet plane, I believe. And still miss his presence, an environmentalist, singer, and had the marvelous opportunity to watch him perform live in Colorado. It was really enjoyable. John Denver. Sunshine on my shoulders, of course, leaving on a jet plane, just a host of songs that have become nearly part of our culture. We're spending time in section 7.5 to start and 7.4, and that deals with converting from American to metric and back the other way. For most of us, it's trying to take something that we are familiar with and to an unfamiliar, because we don't live in a society where the metric system is part of our everyday experience, but we use dimensional analysis. So that's where I'd like to start first, is 7.5. The quiz that we are going to have today will focus on 7.3, 7.4, 7.5, dimensional analysis, and I think you'll find it pretty darn straightforward in the same spirit of what we've been doing the last couple days in class. So questions on 7.5. Is there anything there? Okay, Michael? Okay, it's from meters to yards. So let me go to the board. So we want from meters to yards. And is there a particular number of meters?
Yes, 3,000 meters.
3,000 meters. And by the way, 1,000 meters is a kilometer, so we're basically going from kilometers, 3 kilometers to a yard, but we can take it just as is. And I want yards. Okay, I'm going to try to get that so it looks somewhat level on the board, even if it isn't by what you're seeing. Okay, the question that Michael's asking, depending on the conversion you use, will you get different answers? As long as we're consistent with the conversions and that they are reasonably accurate, we should get the same result. Now I say should to the extent that there are round-offs involved. And so it might have a very subtle difference, but it shouldn't be something that messes an answer, but we'll see. So we want yards. So I'll start here. Now since I want yards and I have meters, I probably would like to go to the miles because we have that connection between the miles and kilometers. So that would be my guess. Now, if we remember 1,760 yards is 1 mile, and that came out of our dimensional analysis in the Math 10, but that's where I think I'll start, and I'll have that as 1 mile. Because I know something about the number of kilometers in a mile. So every mile, and again, all you have to remember is that which one is the larger of the two. If you're going 55 miles per hour, remember it's that 89 kilometers per hour in the Fibonacci sequence. So I'm going to have here that 1 mile, and now this is where I say there's a round-off involved, because technically I'm just using 161, and I used 1.618 for what we were doing, but I would have rounded off to 162 in terms of kilometers. Now, what is your third digit that they give in the text for the number of kilometers in 1 mile? It's a 1.6 what? 19? 09? So 16109, so the 161 to me, I wouldn't go any further than that. And so, yes, if you go further, you'll get a slightly different answer. But it shouldn't affect very severely a comparison you're going to make with an answer on the computer. Well, I still have a bit to go because I have 1 kilometer is equal to what? 1,000 meters. And then it's just multiplying in this last one now by 3,000 meters over 1. Now, there are clearly other ways of doing this, but if I try to limit the number of equivalences that we memorize, this seems like a nice balance. So I look at my numbers I have left, 1760, a 1, and a 3000. And then, of course, here's the magic of doing it in a immediate conversion. Your 1,000 into the 3,000 just went 3 times. So, I mean, you're there immediately. Now, this is going to be in terms of yards. And this is the pesky part, because you're trying to divide by 1.61 or 1.6109, and that just sucks, doing that division. Now here, well, you're just at 5,280. I mean, because the yard was dividing the mile in feet by 3, so you're back to 5,280 over a 1.61. And that's just going to be a long division that's rather miserable any way you cut it. Is that far enough?
Yeah. I just use a different, I use 1 yard to 1 meters.
You could use a different conversion as long as you want to memorize that particular one. But I'm finding that for me, the fewer I have to memorize, the less of an impact it is on me, and I let the dimensional analysis carry me through. So again, the list. What we're saying is 1.61 kilometers for 1 mile. And then on the small version, 1 inch, 2.54 centimeters. And then we had the 1 kilogram at 2.2 pounds. And we have 1 liter was 1.05. I guess it was a 7 quart. And I'm finding that if we just limit ourselves to those, we cover everything with dimensional analysis. Pardon? Well, it's the one, okay, it's just because the 10 has not been that recent. It was the golden mean. And we said when we did Fibonacci numbers that if you were at 55, the 89 was the metric version. We said that ratio is 1.618 as the golden mean, and I mentioned at the time that is extremely close to what we would get with the formal. Well, it disagrees in the third digit. So instead of saying 1.618, we just say 1.61. And these, along with the other ones we know, make it really easy. And if you remember that milli means 1,000, a centa is 100, a deci is a tenth, then the others, the kilo for 1,000 times, and your deca for 10 times, and your hecto for 100 times. Just remember Hector. Consider him 100. He will not appreciate that. But I'll have to tell him that we're using his name in vain. That we'll remember Hector's age at 100 and we'll just multiply by that. Okay, Michael. Another problem from 7.5? Yeah. Okay, let's go with it.
Okay, it's a 9/16
9/16 drill bit.
Yeah.
To millimeters. Okay. Of these 3 up here, which one do you think I'm going to focus on? The second one, right? Okay. So let's see what we have here. I think I'm going to maybe crowd that in up here. That looks more or less. And I think I might get by with very little here, but let's see. Now I'm wanting it in what? Millimeters. Now again, my argument, you start with what you want. So 1 millimeter. Now, in fact, I'd better not put 1 there because I note that I'm in terms of inches, right? I want millimeters at the end, and I have centimeters involved in between. So I could say that 10 millimeters is 1 centimeter. Then 2.54 centimeters is 1 inch, and then I have 9/16 inches over 1. Now again, with these decimals running around, I don't gain a whole lot in this process. I guess I could argue that this is 254 over 100. Then I could cancel others. I could look at this as 10 times 254 over 100 times 9 over 16, and that's going to be, I should have put I in here if I'm going to be consistent. That'll be in terms of millimeters. Now the question is whether or not you want to do that kind of simplification, or otherwise I can say 10 into here, and that goes 10. And then the 254, I know it's divisible by 2, and so I could possibly say, okay, I'll take 2 into here, get an 8, and 2 into here is going to go 127, correct? But 5 won't go into 127, and 2 won't go into 127, so that's as far as I can reduce it. So it looks like I'm going to have to divide 80 into whatever this product is. So 9 times 27 is a 63, carry a 6, so 24, that gives me 11, and divide by an 80, which is going to be in terms of millimeters. So again, 9 times 7, 63, carry a 6, add 18 and 6 is 24, carry a 2, that gives me 1143, and I would personally be dividing by 8 and then move the decimal one place to the left. Otherwise, if you're dividing by 80, first divide by 8 and then divide by 10. Dividing by 10, you move the decimal one place to the left. Or just divide by 80. What I'm saying is if I divided 8 into that, it's an easier divisor. I can do short division. That's 1, 3, 4, 23, so that's going to be a 2, and that's going to leave me a 7. So if I run that as a decimal, that's going to go 8. That's going to be a 64, 6, 8, so that will be 3/4, so a 7/5. And now I have to divide by 10, so it appears to me that I'm going to have this at 14.2875 millimeters. I just prefer to divide by 8 than 80. So if I divide by 8, then divide by 10, and I've done the same thing. Okay? Any other question on that problem? And again, the part that's really of interest is up here. The rest we're doing a Math 10 arithmetic problem, which is nice to review. And it's sort of a feel good to get a solution. Anybody else in 7.5? This is just, these are problems from 7.5. Okay, then I'm going to go to 7.4 because there were some questions there. So this is now section 7.4. Well, let me take something from 7.4 and then I'll come back. Any questions from 7.4? Kim, I didn't know if this is where you had a question or...
I'm just having a hard time remembering which way to move.
Okay, the question of which way to move the decimal. And here's where I'm disagreeing with the approach in the book. I don't worry about which way to move. I use dimensional analysis. I just need to know that 10 millimeters, let's slide over here for a minute, Chris. When I had this as 10 millimeters, I knew that that was going to be 1 centimeter. Now, it helps to have in mind that a millimeter is about the thickness of a dime. And a centimeter is about what? The width of your pinky. That's the one I've always used. It's the one that's used in the text. So how many dimes on the edge can you stack on your pinky? And that gives you a way of looking, oh, I got 10 of those on there. So if I see in the middle of the test going, 10 of those, then I know that you're not counting your fingers, but you're counting how many dimes you can put in the tip of your finger. let dimensional analysis do that for you, rather than remember which direction you're moving. The thing that I would, if I were writing this material, and I've not had a particular desire to write a pre-algebra, I would build on my experience of trying to teach the 10. And if there's one thing that's very clear in the Math 10, trying to decide whether to go right or left is a disaster. I battled that for year after year, trying to get it so people remember when you go to the left, when you go to the right, and it doesn't go well. Anyway, I package it. Well, then if I'm going to try to build on this in the metric unit and say, well, you got to go this far to the right or that far, no. It's not going to fly. Dimensional analysis works. Let it do the walking for you, and it'll dictate what should occur. So let's take a problem that you're bugged by, and let's see if we can make some sense out of it without having to remember whether we're going right or left or in between. Okay? Yeah. 0 point, I need to get that larger, 0.26 liters to cc's. Now, there is, and I'm going to come back center here for a moment, Chris. I need to do some housekeeping here with the computer before it goes completely off on me, because I'm concerned if there is a request that I need to reference the web page, so let me do that momentarily. And then while I'm here, you just have to appreciate Bill Gates every time you hear that. If they ever do an operating system without those charming, call it charming music, I don't know, at some point irritating. I'm not sure what I'd do. I'd miss it. Now, a cc is a milliliter. That's just one of those things that you need to put in your head. 1 milliliter, 1 cc. If you take a cubic centimeter and filled it with water, a very small pinky thimble. So it's the little thimble you put in your pinky, and you fill it with water, you got 1 cc, 1 milliliter. Okay? So with that, as we come back here, they're considered the same. That's an equivalence. 1 cc is equal to 1 ml. But that's exactly where I'm going to have to start. And on most of these, I think you find 3 fraction bars does it. That's sort of nice. A lot easier than some of them that we had in how much. So I want cc's at the end, and that's not a community college. That's a cubic centimeter. Okay, just want to let you know. And that's equal to 1 ml. Well, the minute we do that, we're home free. Because milli means 1,000. So if I'm wanting to get to liters, 1,000 of these mLs is what? 1 liter. And I had 0.26 liters over 1. Done. And you never did have to decide which direction you're going. Okay? True? Before I go on, Marisol. There are a lot of things you can do. The question is, if I just multiply by 1,000 and don't use dimensional analysis and I get the right answer, is that okay? Yes. My track record with trying to explain whether you go to the right or the left and remember that all the time correctly isn't good. But if I say to you, use dimensional analysis to do it, you no longer have the choice. Fair enough? So if I say use dimensional analysis, I want it set up this way. And guess what? On the quiz today, 3 problems. They each start with the following. Use dimensional analysis to, and then make the conversion. Okay, so what do I have? Pretty easy problem. 1 times 1,000 times 0.26 over a whole product of 1. That's going to be cc's. And so we have 260 cc's. And you didn't have to decide which way to go. No decision process. You let the mathematics do the work. Other questions on 7.4? Going once. Like I'm in an auction. Going twice. Okay, we're back to 7.5 with another question from Michael. And Chris, if you'll go to the other board with the camera, I'd appreciate that. Michael, is this another computerized version? Okay. Okay, read it to me first. I'm not going to write because I'm going to have to go over there and I need to have, go ahead and make your move with the camera. I want camera 1 on me here, 2 free to the side, if you would, Chris. Thank you. Now.
25 milliliters.
Okay, milliliters to ounces. And again, I don't play the game with cups and pints and all the nonsense that goes in the presentations for the computer problems. Okay, so I'm going to leave this on the board, and I'm just going to disappear momentarily, go over to where Chris has the camera on the side, and again, I'm going to let dimensional analysis do what I need to do. Okay, so Michael, again, it was start with, give me the number, 25 milliliters to ounces. Okay, now with camera 1, if you would please, Chris, right below the clock in camera 1, you have the 4 equivalences that we just talked about. So if you will go to that, and the last one there is the 1 liter is what? 1.057 quarts, and that's where I'm headed. So let me take a look at what this, that looks pretty level. I think I'm going downhill, beat bang, but it looks great on TV. I feel like I'm going downhill, uphill, or something like that. Okay, so I want ounces here. And the equivalence, again, was the liter and the quart. So what I'm going to do is simply take my 32 ounces, 1 quart. And then I have what? The 1.057 quarts, 1 liter. I have 1 liter is 1,000 milliliters, and I have 25 milliliters. Now, this one happened to go a little bit further because I have how many? 4 fractions. But I can do it. Okay? And I don't have to memorize a half a dozen different equivalences. Keep it simple. Paucity. As few symbols as we can, as few equivalences as I can. Now, 32 times 1.057 times 1 times 25 over 1,000, and that's going to be ounces. Now, that's the hard part. Now, the rest, I'd leave the 1,000 alone, quite honestly, because I can just move a decimal 3 places to the left when I'm done. So I'm going to come back here, and I think this is one we talked about, because I remember saying 32 times 25. Okay, because you have a 32 times your 25. 4 25s is 100, so that's 800. So I have 800, and I have it multiplied by 1.057, and then I'm going to divide that by 1,000. So I'm tempted to cancel, but I won't. These zeros are sort of nice to put down. Remember, we had those shortcuts before. Then I have 56, 45, and an 8. And I have 3 digits there, and then I'm going to divide it by 1,000, so 0.8456, and I have ounces. Also, probably, as we slide over there a little bit, Chris, that would be probably written as 0.85 ounces. Okay? And that was one from the book. So this is from the computer?
Yeah.
They took one from the book for the computer, because we did this with the class. Oh, that's not kind. Michael's saying he missed a problem in the computer, and they're supposed to give you a new, different one. And they gave you the same one. Okay. That's not supposed to happen, but that's a nice to know. I'll put that in my memory bank. as are part of Sarah's discussion with me about computers. And
Also, I've had one where you should be rounding up and it goes down.
okay, so you have some problems where you should be rounding up and it rounds down, although I guess it's truncating. Just throwing the digits away. That's called truncating. Throwing the digits out without rounding off, period. Okay, so again, don't want to beat a horse that we've beaten before, but the idea that we are, battling much too often the idiosyncrasies of a computer. Other questions on 7.4 or 7.5? Sandra, yes? No, we're back to bashing the computer. Okay, go ahead.
It's just that when we had like an example of like it had the divestment step, the way we set it up is we start with what we want to end with.
Okay. In the computer, to do dimensional analysis, they are not doing what I ended up doing in dimensional analysis in Math 10. And they usually, at the end, have what you want, and I say start at the beginning. Well, let me tell you the metamorphosis of that. When I first did the dimensional analysis unit, I did it very similar to what's in your book, and it didn't work. I battled that semester after semester, beating my head, and finally one day said, okay, let's try it another way. I'm going to start with what I want at the end. See if that works. Suddenly, how much unit? Worked. So, all I can say is my experience of semester after semester with dimensional analysis worked a lot better answering the question, what do you want? And then put that your first fraction. Now keep in mind that multiplication is community. So I can rearrange those products any way I want. So all you want to do is just see if what is in your book matches the same factors that you have. The fact they're rearranged should not upset you. Okay? Easier said than done. Now, that was the statement about the computer. Now, do you have a question about a problem? Okay, oh, we're back to temperature. Okay, what is it that you want to do? That's not a person, I hope. A person didn't have an 83 degree, right? Oh, okay. Okay, I thought maybe a person had dropped to 83 degrees Fahrenheit. That would be pretty serious, right? And we want to go to Celsius. You weren't here to hear what I said about this. So I'll say it again. We know that if you want to go from Celsius to Fahrenheit, it's like going from miles to kilometers. You get a larger number. Now, when we went from miles to kilometers, we used 1.6, roughly. When we go from Celsius to Fahrenheit, which has nothing to do with what I've written up there, Celsius to Fahrenheit, it's 1.8. So I just take my Celsius and multiply it by 9/5 and add 32 to get a Fahrenheit. And that's the only one I memorize. Now I substitute. Okay, so I have 83 degrees here, and that's equal to 9/5 C plus 32. Welcome to an equation. Now you've spent the last 12 weeks learning how to handle that equation. You subtract 32 from both sides. So I'll do this. And we typically, at this point, make this change without showing it. And so you would just say, well, I had 51 was equal to 9/5 C. But you know how to get rid of this factor. You prefer, I think is your choice, dividing by it. But James prefers multiplying by the reciprocal. Either way you play the game, I'm going to put C on this side and say that I have 5 over 9 times 51 over 1. That's going to be my answer. So, nothing reduces there. So I'll take this, and that's going to give me 255 over 9. So I'll divide 9 into 255. It's going to go 2. I'm going to have the 7 left. That's going to go 8. That's going to be a third. So I have 28 1/3 degrees Celsius. Now, you have an option of memorizing 2 formulas if you want. I like taking 1 instead of 2. But if you want to double your pleasure, memorize 2. You have a look that's not following what I did. Where is your question? You have a formula, you start here, you substitute and solve. Formula, substitution, then solve. Any other question? This is still 7-4? Is that correct? That's a 7-5. Okay. Still taking 7-4, 7-5. Nobody wanted anything on 7-3? Okay, so 7-4, 7-5. We are done with the questions. Everybody's happy now? Okay. I'll leave this. I'm going back center. Okay. I'm going to cover something here that I don't want to technically do as a section. But it is something that, interestingly for us at our school, when we started asking what did we want in a pre-algebra, this dictated what I did in Math 10 with medical dosage problems. Because the state board exam in medical dosages asks people to solve what we call dosage problems. And traditionally they were done with proportions, and it gave considerable problems. So we actually created a course here for a few semesters where we did, for the nursing program, dimensional analysis to solve those problems. So I want you to turn to 563. And this is section 7.6 that technically I don't want to go into great detail, but I want to just look at a typical kind of problem. Okay. And number 25 I have on the document cam now as we go to that. And let me bring it in a little bit tighter. Okay, now you're going to have to get used to this. A patient with a mass, and we aren't talking about something like a tumor. We're just talking about their weight, okay, but independent of gravity, if you will. So it's a mass of 55 kilograms, okay, and this patient is supposed to get so many, and it looks like ligrams, but it's milligrams, okay. And so what I need to do here, it's 9.5, so the order is to administer 9 milligrams per kilogram. Okay, and this person then weighs or has a mass of 55, and the question is, how much of the antibiotic should be given? So I'm on page 563 and looking at a particular problem here. So let's just leave that up on the screen. And they usually, quite honestly, had a lot more to do with the kind of thing that as we come over here, let's just slide over with the camera for a moment to here, where we had so many milliliters to ounces. So I'm going to come back to the problem in the book in just a moment. No, I need you back here, Chris. Okay. We had so many 25 milliliters to an ounce, or going to an ounce. That was the kind of thing that was done with dosage problems. Can you slide over a little bit more, Chris? I need to see the 25. Thank you. This was the kind of problem we did in a dosage class, because you would be going both ways, ounces and milliliters, and so that was a very typical problem. Now as we slide down this way, using the same idea, so just pan with me, well, follow me. Okay, I feel like a John Denver tune, follow me wherever I go. So the dosage as we come back to the document cam, is, okay, I know what this is at 55 kilograms. And what is the dosage? It is, what is it? 9.5 milligrams per 1 kilogram. So this was the dosage rate. And to argue, as we go to the board now, that this is dimensional analysis, it's an oversimplification, correct? But you can see what you should do. The kilograms go out, you multiply 5 times 9.5, and you're done. Now, that's not a very serious dosage problem compared to what we had in our first one. Now, what oftentimes is done in problems a little bit more interesting than this is where you have the dosage for an IV. So instead of being something in milligrams that you're going to take orally, you might have something in an IV that you're going to have so many milliliters per pound, and then you have so many drops per milliliter for the IV rate, and then you have, usually that'll be drops per milliliter, then milliliters per kilogram, and then you have a young child with so many pounds in weight. And you do those kinds of conversions. That would be a little more realistic. So let's leave this here for a moment. I should just erase this last fraction because I didn't use it. Let's see if we can find anything a little more substantive, because that was just too straightforward, too easy. So let's come back center. I'm looking down at number 32. Okay. And that's drops per minute, and that would be how many drops per hour. I'm trying to find something that's not going to require that I go any deeper than I need. And I'm looking here. I'm missing a particular symbol that I don't remember off the top of my head, so I'm going to go back to, yes, here we go. This is example 6, 559. And this is what I'm trying to get at. These are 559, example 6. So a patient is to receive 500 milliliters of a 5% dextrose water solution as an IV over 4 hours. Okay, and in this process, the label indicates that you have 10 drops per 1 milliliter, and how many drops should the patient receive each minute? Get the idea? Now, if you just look at that, as we come off there, let me just read it again as you listen. And when you hear this and then try to say, how would you do it in your head? It's confusing enough that I don't think without setting it up as dimensional analysis, it's something that you're going to want to do, particularly if it's under the stress of an ER. Now, this particular problem is of interest to me because this was pretty much the kind of problem that I remember with a 6-week-old baby who was having surgery and having the nurses argue what the drip rate should be. And when it's your child and they're arguing, it was time for a lecture on mathematics. And so I proposed a solution based on dimensional analysis, and I don't know to what extent it was appreciated, but I felt a lot better. So, okay, coming down to the problem again, we have, well, they modified. Now, we have 500 milliliters is what the patient's to receive. And we want to know how many drops, what's the drip rate per minute? You get the idea? So you're wanting how many drops per minute. That's what it means to dissipate. And you have 10 drops per milliliter. So as you look at that, in terms of the ratios down here, they're setting it up here as 10 drops per milliliter, and you know that You want to have 500 milliliters over what? 4 hours. Because you want the whole bag to be done in 4 hours because that's when the shift changes. Now, I'm being a little bit sarcastic there, but in reality, we come off there now, there are many things that are done just for the convenience. So if a quarter of a tablet is what you want to give, then it's an approximate solution for the person's weight. There is a much better formula you could use that would be fine-tuned for a person's weight, but you aren't going to give a third of a tablet, you're going to go a half or a quarter. People just can't break tabs into thirds. Although I've seen now some neat little pocket machines that my aunt used where she would be able to put a tablet in there and break it into 2 parts or 4 parts. I haven't seen anybody get clever enough to do it with 3 parts. So the question, how do you go from one to the other? And as I come down to the solution here, and this is what we're talking about dimensional analysis, you have 500 milliliters per 4 hours, and this is where I would totally disagree with the setup. What should be done? I would immediately go to the hours and the second fraction over minutes, okay? But the key here is that you're wanting what? Drops. 10 drops per milliliter. That was a 1. The first one is a 1. And then 1 hour was 60 minutes, and it left you with what? So many drops per minute. Now, this gets back to what Sandra's observing. So let me come off there for just a moment. The book's sliding and the camera head's not staying where I want it. Let's come back to that. And the question, if you were to do this, and keeping in mind what we've said about what you want at the end. Okay, so I'm going to, again, just come with a set of fractions. And we'll come off the book here in just a moment, but let's leave it there. Now, I want to have the drops per minute, correct? So that's where I'm going to start as we come off there now. Drops per minute. So I would start with drops. Now, I have something in the problem that tells me, in the information given, how many drops per what? It says that there's 10 drops per 1 milliliter. Is that correct? Okay, 10 drops per 1 milliliter. So I would start with at least the drops I want. Then, as I come back to the problem, and I'm looking at the original statement of the problem, I had something with hours involved, correct? So I would be inclined to say, in terms of what I have there, that there were so many milliliters per hour. Come back there one more time again. So I have the 500 milliliters. Makes sense at this point because what's going to happen as I go to the board? The milliliters would now cancel, so I needed that. And then that, 500, thank you. And then that's going to be what? Over the 4 hours. And so clearly the process is working. And so then I have 1 hour over 60 minutes. The hours cancel, and now the process we talked about. Start with what you want in the numerator. And you wanted it per minute, and it gives me this order, which is still the same problem, but you're doing it logically. And that's what I'm trying to argue, again, rather than the presentation that would be done in the text, because I end up with what? 10 times 500 times 1 over the 1 times the 4 times the 60. And in doing this, there are a couple, and by the way, this is going to be drops per minute at this point. This is called the drip rate. And so, as I look at this, as we bring that a little bit tighter, if you could, Chris, because that's a little bit too hard to read in the television. I know that I'll just move over a little bit tighter, bring it a little bit tighter. Now, what do you know about 4 and 500? You don't. 4 goes into here 125 times. And then 10 goes into here, giving me a 6. So now I have 125 over 6, which is a drip rate of what, roughly? 20. 6 times 20 would be 120. And so I just say, okay, I'm going to run 120 drips per minute. So that means, and if you're going to sit there, you aren't going to do 120 drips in a minute. You're going to say instead, how many would it be if I have 20 per minute? Then how many should I do per second or per 10 seconds or something? I don't think very many people are going to sit there and fine-tune that waiting for a full minute to count 20 drips. They'll go 10 in 30 seconds. They'll go 5 in 15 seconds. And then you'll go from there. So this is roughly 20 drops per minute, or you might say 21 drops per minute. Now going back to the text, and I can't read that as carefully. I think it says 20 to 21, correct? Yeah. Okay, so as we look at that, technically, as we come back to the book now, it's giving the figure at 20.83, so if I round off to the nearest drop, 21 drops per minute. Now, the point I'm bringing up here as we come off there now, that was our motivation here as a college, to create something with dimensional analysis. And we actually went through a period where we felt strongly enough about this for the nursing program and the science curriculum that we modified our Math 70, our beginning algebra, so we had a unit that we handed out on dimensional analysis. Then we decided to change to a book that included dimensional analysis, and then I started incorporating it in Math 10, and we do okay as long as people take 10 or 20 before they take 70. For the student who's coming out of, say, the high school programs, and they just test into 70, I suspect that 95% of those people wouldn't know a dimensional analysis problem if you put it in front of them. So there really is a need for us to do what we did for a number of years, and it just sort of got lost in the shuffle. So that is what's missing in 7.6. Now, 7.6 would be interesting for us because they are reasonably better problems than anything else we've seen in the book up to that point. The rest of this section on 7.6 has to do with mortgages and such and real estate problems, and I just can't defend that as a pre-algebra kind of content for any of our programs. For nursing, the dosage problems make sense, and for the science classes, again, it makes sense what we're trying to do. Because we do drip rates, by the way, for titration when you're in a chemistry class. And so that's, again, doesn't just have to be done with IVs. But if you see a nurse at your bedside checking the drip rate, you'll know what's going on. Okay? Where do we go next? That's what I've said. I don't think there's any more questions, and I don't want to belabor this section 7.6. We said we're going into Chapter 8. I want to look at something as a kind of advanced organizer is the technical term in education, okay? An AO, advanced organizer. I want to go back to how we did percent problems. This is a discussion that Sarah and I had at dinner last night about percent problems and what we do in the 10 and what's done in this text and in terms of proportions. So what I'm going to do is fast forward to section 8.4. And the title of this, as we cut to the book, is Solving Percent Problems with Portions. Not proportions, but portions. That didn't set too well with me, but let me come back to what I'm getting at. Portions of food. Well, maybe. I'm going to be here. Here's the formula. One of two ways of doing a problem with percents. This is the formula. Percentage equals base times rate. Agreed? And this is just old hat. And we said if you wanted, you could solve for R, or you could solve for B. You divide both sides by B, and you get that R is equal to P over B, the part over the base, the part over the whole. And then we said that you could solve for what? For B and have the part over the percent. P over R. Those were three formulas. This is the triangle in essence, because this was focusing on a formula and rewriting it in two ways. My argument paucity. One formula gives you three. 3 in 1. The other approach to this was to go ahead and create a bit of a triangle. Well, so much for my triangle. And we said the base of the triangle, or the whole, would be down here, correct? We called this the percent, and we called this the part. Now, this is interesting because this is the same language that's used in the Math 20 text we have, and I'm very comfortable with that. And we said that you had divisions here, and you had multiplications here, and so you covered whatever you didn't know. So, in a sense, we are saying that this percent is equal to part over whole, correct? Now, if the letter, and this is where I wish the P that we use over here, what we call percentage, was not used in the text as it's going to be, because the letter P should stand for what? Percentage or part, not percent. So let's say you have your percent as some letter R as a percent. So the point I'm making, this becomes R over 100 equals part over whole. So instead of calling R as a decimal, R is your percent, but with a percent sign. So I'm going to think of R percent, not as a decimal. So that means R over 100. Sliding over now, Chris, just to here and pull it in tighter. And move a little bit more so we get a little bit of blue. I'm going to have to be over here in the blue part. What do we call this when we get two fractions equal? A proportion. So you're going to know two of these three pieces, correct? And the 100 sits here. So you ask, what is it I don't know of these three? You put the other two in, and how do you solve a proportion? Cross multiply. So if I look at the problems we did in the percent unit in Math 10, and I just treat this now as a proportion, I've got a very nice way of solving percent problems. So if somebody says, gee, I got a 20% discount. Remember that problem? You get 20% discount on airline tickets. So I have 20% discount on airline tickets, and I got back $125. What was the original fare? Bingo. A proportion. Cross multiply. 20W is equal to 125 times the 100. W is equal to 125 times the 100 over what? 20. You simply cancel, get a 5, and so the answer is $625. Not bad. That's the only difference in this approach with what we did. Now, the reason I don't go here, I don't want to get into cross products and getting into equations, but since this is what pre-algebra is about, this is a logical extension. And so I'm hoping as you look at this, you say, hey, that's not bad. If you look, as we are going to on Monday, Tuesday, and Wednesday, if you look at 8.1, 8.2, and 8.3, it isn't going to be hard. So with that, we're going to close down here in our usual about 2 minutes at the end. And we're going to go to music here momentarily with the choice, and we're going to go back to John Denver.